In this video, we're going to look at some more examples where we're using sigma notation to help us simplify expressions involving sums, and we're going to use it also to explore the relationship between the terms in a sequence and the partial sums in the corresponding series. All right, so the first thing to note is that when you're dealing with finite sums, as well as convergent infinite sums, we're going to be able to use certain algebraic operations to rewrite the sum. So let me bring up a snapshot of the textbook here, where you have a nice table here in 10.2. It's called the linearity of infinite series, and it says the following, that if you have a sum an and a sum of bn, and they're both convergent, okay, and that could be, they could converge because you're only adding up a finite number of things. If you're adding up a finite number of things, you automatically are something finite. Or it could be that you're adding up an infinite number of things, but it actually still adds up to something finite. What they're saying is that we can, first of all, conclude that the sum of an plus bn, or the sum of an minus bn, and the sum of any constant times an will also be convergent. And beyond that, we can also split up the sum. If our terms involve a sum of two different sequences, well, we can think about the individual series separately. The sum of an plus bn is the same as the sum of an plus the sum of bn. Same thing for differences, and for some sequences that are made up of a constant times another sequence, we can factor out the constant. Now, none of this should come as a huge surprise to any of you. We've been doing these same sorts of operations with derivatives and with integrals for quite a while now. But the important thing to recognize is that we actually shouldn't just assume that these things work. There is a stipulation here. This is only going to be true if the sequences and series converge. Okay, so the sum of an and the sum of bn must converge before we can use these sorts of operations. But now that we know that we can do this for convergent series, let's look at a couple of examples where we can use that to help us simplify matters. All right, so let's first of all look at an example. The sum of 2 over n squared minus 3 over n plus 1 squared from n equals 1 to infinity. And let's apply those rules to try to get this down into a nice simple form. So first of all, notice that we could divide this into two sums since we have a difference of two sums. And for this case, we haven't learned the techniques necessary to show that these individual terms will converge, but we're going to take it on faith that they do for now. But later on in the course, you will actually need to check to see if things converge before you do this. But we're going to assume that this and this, we call that an and bn, that those two terms separately lead to convergent series, in which case what we can first of all do is write this as the sum of 2 over n squared from n equals 1 to infinity minus the sum of 3 over n plus 1 squared from n equals 1 to infinity. Okay, so we've divided it up into two sums, and both of those have a constant factor that we could bring outside here. So we can write this as 2 times the sum of n equals 1 to infinity times this, and that's going to be the sum of 1 over n squared, and it'll be minus 3 times the sum from n equals 1 to infinity of 1 over n plus 1 squared. Okay? So, let's see, what else could we do to simplify this? Well, notice that that second sum has an n plus 1 in it, and that n plus 1 is squared. If we wanted to, we could try to shift the index of that sum to make it look a little bit more like the first term. So let's do that. Put this off to the side. We have the sum from n equals 1 to infinity of 1 over n plus 1 squared. Let's see if we can write that as the sum of 1 over n squared, so that it looks like the first term. And then the question is, what value of n would we need to start with? And over here we had an n equals 1, which when you plug that in, you get n plus 1. So that's going to be starting with 2. And so if we start with 2 over on the right, then we should get the same starting point. And if we have an infinite number of terms, then we'll still want to go on forever in the second case. And so we can actually, there's a little sidebar, we can write that second sum as the sum from n equals 1 to infinity 1 over n squared minus 3 times the sum from n equals 2 to infinity of 1 over n squared. And so notice that second term, that looks a whole lot like the first one now. The only difference is that it's missing one term. The original sum started with n equals 1, and the second one started with n equals 2. But if we get a little bit clever here, we can actually even simplify this further. Notice that the sum of 1 over n squared from n equals 2 to infinity is the same as the sum from n equals 1 to infinity, except for the fact that this would include an extra term. So if we subtract off the first term, that would cancel out the n equals 1 case. And so those two things are exactly the same. And so we can plug that in here. So the second term can be written as the sum from n equals 1 to infinity of 1 over n squared minus 1, where we're just subtracting 1 to remove the first term. It's kind of like we put it back in since it was missing in the line above, and then we took it back out again. So the net effect is it's exactly the same as what we had in the previous line. And now we can do a little bit of cancellation here. Notice we have 2 of the sum minus 3 of the sum. So our final answer is going to be minus the sum from n equals 1 to infinity of 1 over n squared plus 3. And if we knew what that sum approached, that would allow us to actually finish this problem off without a whole lot of work. Unfortunately, that's a pretty tricky problem. We will talk about the answer to that sum later on. It actually took mathematicians quite a while to sort that one out, and the answer is not exactly what you would expect. All right, so that's one thing we can do. We can apply these rules of linearity to split up sums within the terms. We can pull out constants from sums, and we can also, as we saw in the previous video, shift the index to combine things. We can also try to relate partial sums to the full, to the individual terms in the sequence. All right, so let's look at an example. Let's suppose we're interested in the sequence an equals 1 over n minus 1 over n plus 1 for n equals 1, 2, 3, and so on. Let's see if we can find a formula for Sn, the nth partial sum. Okay, so let me remind you that when we write Sn, what we mean is the sum of An, or Ak rather, up to n. We had a starting value of 1, and so we're going to be adding up A1 plus A2 plus A3 all the way on up to An. Okay, so let's see if we can find a formula for the partial sums given what we know about the individual sums. Okay, so to start out, it might be convenient to actually write down the first couple of terms. And so let's write out, first of all, the Ans. We'll write down maybe the first 3. A1, according to this formula, if I plug in 1 up there, I'll get 1 over 1 minus 1 over 2. A2 is going to be equal to 1 over 2 minus 1 over 3. And A3, if I plug in a 3 for n, I'll get 1 over 3 minus, and then notice the denominator of the second term always seems to be 1 higher than the first. Now, I'm going to deliberately leave those terms as is, rather than trying to find a common denominator, because I want you to notice what happens when we start trying to add them up. So S1, the first partial sum, is going to be 1 minus a half. It's just the same as A1. But S2 is A1 plus A2, which is going to be 1 minus a half plus a half minus a third. And notice that we have a minus a half and a plus a half. So that's going to cancel out. And we're going to be left with just 1 minus 1/3. Okay, so we'll continue on. S3, it's going to be A1 plus A2 plus A3. And again, if we add them up, we'll have A1 plus A2 plus A3. And again, the middle terms seem to be canceling out because we have a minus a half plus a half. We have a minus a third plus a third. And so this is going to be 1 minus 1 over 4. And that pattern is going to continue. If I add another term, notice the next term will have a 1/4. That's going to cancel out that negative 1/4. And if I go on, the next term would have a 1/5. That will cancel out a negative 1/5. And so if we continue the pattern, it looks like the nth partial sum is going to be equal to 1 minus, and notice for S3, we had a 4 in the denominator. For S2, we had a 3 in the denominator. For S1, we had a 2 in the denominator. So it looks like if we put an n plus 1, one higher than the term number, that would give us the correct formula that works for all of these. Okay, so by listing off the partial sums, in this particular type of sequence, which is known as a telescoping sequence, you can actually find a nice formula that doesn't involve adding up a bunch of things. It just involves subtracting two things here. And that would be very, very useful because we can find out what the sum approach is now by looking at this much simpler expression. Okay, so we can relate the individual terms in the sequence to the partial sums. We can also go in the opposite direction. If we know the partial sums, we can often find a way of computing the terms in the sequence. So let's suppose that Sn is equal to 1 minus 1 over 2 to the n for n equals 1 to infinity. Okay, let's see if we can find a formula for an. Find a formula for the things that we added up to generate that. Okay, well, to figure this out, let's think about what Sn means. Sn is the sum of A1 plus A2 plus A3 all the way on up to An. And notice that has the thing that we're looking for in it, but it just has a whole bunch of extra stuff as well. So if we could cancel out that extra stuff, then we could find An. So let's write down what Sn minus 1 is. Notice that's the same thing, only instead of stopping with the nth term, we stop one earlier. And let me rewrite the line above just a little bit. We could write this as An minus 1 plus An, just to be explicit. An minus 1 is indeed in the line above. And now notice the second line is all the stuff that we wanted to get rid of from the line above. So if we subtract these two things, what would we have? Well, the A1s would cancel, the A2s would cancel, the A3s would cancel all the way down the line, and we'd be left with just An. That's the only thing that is missing. Another way to look at that is the sum from k equals 1 to n of ak minus the sum from k equals 1 to n minus 1 of ak is just equal to an. If you add up all the terms from 1 to n and all the terms from 1 to n minus 1 and subtract them, only one is going to stick around. And since we have a nice formula for Sn, we can use that now to compute An. An has got to be Sn minus Sn minus 1 which is just the ones will cancel and be left with 1 over 2 to the n minus 1 minus 1 over 2 to the n. Okay? So taking a difference between consecutive partial sums just gives us the terms in the original sequence that produces the the series. All right, we will stop there and look at some more in the next video.